Okay, we can start. Okay, let's move on to the next talk. It's a great pleasure to have Pratyusha Chowdhury from a local person from University of Southampton. She'll talk about renormalization of conformal correlators and its implications, please.
Hello everyone. So I'll be talking about renormalization of conformal correlators and its implications. This is based on an ongoing work with James Drummond and Kostas Kenderis. So I'll start with a very quick overview of CFT. So a CFT consists of a spectrum and a set of correlators. A spectrum is a set of numbers that characterizes the states in the Hilbert space of the CFT. Now, through state operator correspondence, each of these states can be associated to a local primary operator, which we denote by OI, and with a scaling dimension delta I. Now, once the spectrum of this CFT is known, all the 2 and the 3 point functions of the CFT can be completely fixed up to an overall constant just from the conformal symmetry. Here I have the expressions for 2 and 3 point functions for scalar primary operators. Now, these conformal correlators also satisfy commutative property, and we have this operator product expansion. That is, product of 2 operators can be written as sum of operators through these OPE coefficients. Here, the sum basically runs over the spectrum of the CFT. Now, the set of the spectrum and the OPE coefficient is what we call the CFT data. And given the CFT data, we can operationally compute any endpoint function of the theory recursively. For example, if we have this 4 point correlator, we can take the first 2 correlators, first 2 operators, and apply the operator product expansion. We can do the same thing for the 3rd and the 4th operator, and we can obtain this expansion. Now, if the CFT data is known, that is, if we know the values of P over which we need to sum over, and if we know these coupling constants or the OPE coefficients, we can exactly compute what this 4 point function is, because this expression here in the bracket is fixed by conformal symmetry. But any random set of CFT data does not always give a consistent CFT. We need to check if the CFT data satisfies a crossing equation. So let me illustrate the crossing equation through the help of this 4 point function. So this 4 point function, as expanded here in this expression, is what I have written schematically here. Now I could have obtained this 4 point correlator in a different expansion. So I could have just contracted this first operator with the 3rd one and the 2nd with the 4th one, and obtained a different expansion with different OPE coefficients. That would schematically be this. But since the correlator is the same, they have to be equal. Now, this is the bootstrap equation, and this is a strong constraint on these 3 point couplings or these OPE coefficients. Now, there has been a lot of work on CFT correlators and this conformal bootstrap, but most of these analyses are in position space. That's mostly because conformal group acts more naturally in the position space. But recent work in anomalies or conformal bootstrap, cosmological bootstrap, as Paul was talking about in his review talk, has made CFT in momentum space quite desirable. But we should keep in mind that these CFT correlators in position space are defined for separated points. So when we want to get momentum space correlators, we need to integrate over the position space, and that gives us some divergences. And those are pretty non-trivial, and one needs to completely do a systematic renormalization. I will go through that process with the help of a 2 point function. So suppose I start with a 2 point correlator here. I take the Fourier transform. I will end up getting this expression. For generic values of spacetime dimension D and the conformal weight delta, this expression is well defined. But at special values of conformal weight delta, particularly given by D by 2 plus K, this gamma function will have certain poles, and that would lead to divergences in this correlator. Now, this has to be removed by regularization and followed by renormalization. So the regularization scheme that we choose is similar to the dim reg, just that here we are deforming the space-time dimension with this 2u epsilon parameter, but we are also deforming the conformal weight. So u and v are basically the parameters related to the regularization scheme that we choose. Now once we choose this regularization, we can compute the regulated correlator, and it turns out that this has this divergent piece here. Now it turns out that the divergence that arises for the 2-point correlator can be removed once we add a counter term action having this structure. Here phi is the source that we couple to the operators, and mu is a scale that we are adding for dimensional purposes. So once we add this counter term and add this counter term action to this regulated action and compute the correlator, the contribution from this counter term part, we compute the contribution from this counter term part, and if we fix this counter term coefficient to this value here, it turns out that the divergent piece that we saw earlier cancels, and we get a renormalized correlator given here. Now there is a mu dependence in this renormalized correlator, so this means that the conformal symmetry is broken, and this correlator is now satisfying the anomalous word identities. So the anomaly associated with this can be computed, and this has, like we know in physics, anomalies have always been insightful to understand the theory. So it would be really nice to have a better understanding of these new anomalies that show up from these special divergences. Now the next thing is a 3-point correlator. It was shown in a work from 2013 that a 3-point correlator in momentum space can be written in this triple K integral representation. K is the Bessel function here. Now once we analyze the region of divergence of this integral, it turns out that from this x goes to 0 limit, there will be some divergences that will show up in this 3-point correlator, and this is the condition of divergence for this 3-point correlator that has been derived. So this condition can hold for various possible combination of relative plus and minus signs. So there are essentially 4 kinds of divergences, and each of these conditions can hold separately or in various combinations. So for a specific correlator, when delta 1, delta 2 and delta 3 are fixed, if this condition holds when all the signs here are minus, we say that we have a ultralocal divergence, and those divergent terms can essentially be removed by adding a counter term of this form here. This is similar to the this is structurally similar to the term that we added for the 2-point function, and we saw that and we see that this essentially gives us anomalies for 3-point functions as well. Now a new feature that arises for 3-point function is that when one of the sign here, either one of the sign here becomes positive and this condition holds, we need to add such a divergent term by adding a counter term of this structure. Now this counter term is essentially renormalizing the source that is coupled to this O3 O3 operator, and that will give us beta function corresponding to that O3 source. Now this condition can also hold when 2 or 3 signs are positive, but it turns out that these are not true divergences of the correlator, rather it has to do with the representation that we are using, and such divergences are called non-local divergences, and it can be removed by multiplying a scaling factor with this entire correlator. Now the next most natural thing to look at would be the 4-point correlator. It is the simplest correlator that encodes the dynamics of the theory. So we expect that the divergences that this 4-point correlator will contain will give us some insight into the theory. Now we should recall that a 4-point function is not completely fixed by conformal symmetry. So we need to first fix a theory, and then we need to use perturbative analysis. So for our purpose, we are looking into holographic theories. There has been some work in the context of D equals to 3 holographic correlators. For our work, we are particularly focusing on holographic correlators in D equals to 4. This is because we want to eventually look into half BPS correlators in N equals to 4 SYM. Now for a holographic theory, when we are in the perturbative regime, for a generic correlator, we can have a contact contribution and an exchange contribution. I will get into this in a minute. For this contact piece, it was shown in this work from 2020 that the condition of divergence is given by this expression. Sigma j can be plus minus 1 and n is a non-negative integer. So we are basically looking into the divergent pieces of the contact correlator and the exchange correlator that we compute using 3-level Witten diagrams. So here this is the contact Witten diagram, which has 4 bulk to boundary propagator, and this is the exchange diagram, which has an additional bulk to bulk propagator. Now this integral becomes difficult because of this bulk to bulk propagator, and there are some nested integrals that we need to deal with. Here I have explicitly written down the analytical structure of one such contact correlator. So this is 2244 correlator, and this is how the divergences look like. IJKL here is just to take into account that operators with same dimension can still be distinct. Eventually we can take I equals to j and k equals to m and work things out. Now this 4-point correlator has this C2244, this 4-point coupling. Similarly, we also compute the exchange correlator terms. I have not written them down because they are very complicated and there are many pieces to it. But one thing to keep in mind is that these exchange correlators will contain product of the 3-point couplings that basically arise from these vertices. Now, the last piece in this puzzle is to add the counter terms that will be necessary to remove these divergences. It turns out there are 2 types of counter terms that one needs. So first, if we look at this second block here, these are the counter terms which are added at the level of 3-point function. That is, suppose, let me look at this first term. So this is 045050. Let me ignore the subscripts for now. This 045050 is a counter term which also arises for the 3-point correlator 444, and its coefficient is essentially fixed when we renormalize the 4-point correlator. So similarly, all these other counter terms get fixed at the level of 3-point functions itself. So these all have fixed coefficients when we add them to the 4-point function. Next is the set of counter terms that I have written here. These are essentially fixed when we actually try to renormalize, when we try to remove the divergences of the 4-point functions. So when we add the contributions from the contact piece, the exchange piece, and all these counter terms, and we claim that all the divergent pieces has to cancel against each other, it turns out that we need some relations between the 3-point couplings and the 4-point couplings that I had shown before. But the detailed structure of this relation is still under analysis. So to summarize, here we are addressing this question of holographic CFT in D equals to 4, and we assume that there are operators of integer dimension, for example 2 and 4 here that I showed, such that it satisfies those divergence conditions. Now I compute the 2 and 3-point functions in such a theory, and I renormalize them, and that already imposes some constraint on some of the counter term coefficients. Now next, when we try to renormalize, rather get rid of these divergences that arise in the 4-point functions, we see that there are some relations among the OPE coefficients. But as I mentioned that the result, I do not have any conclusive result yet, so I do not know how the relations exactly look like, but we hope to get some results soon. That's all I had to say. Thank you.
Thanks for the very nice talk. Questions? Maybe I can start. You said it, but maybe it was past one in your 3-point function. Oh, sorry, thanks. In your 3-point function.
Oh.
But yes, yes, here. So K, what is little k in the
Oh, this
condition?
one?
Yeah.
Oh, this is just a non-negative integer. Yeah, right. Like this is
okay.
non-negative
Any
integer.
okay.
Yes, like it's similar to this k here. Like, so
okay,
this is just a non-negative integer. Yeah. Like, so basically whenever this condition, like if I have fixed delta 1, delta 2, delta 3,
yes,
and I have a fixed dimension, whenever this condition holds such that this k is a non-negative integer, it means that I will get a divergence in this 3-point correlator.
Okay, thank you. Other questions?
I have a small question, but more of a clarification question. So I have a question about K as well. So not this K. Actually, can you go to the second or third slide, something like that? Go back. Yeah, here. So
okay.
So here, when you have that right-hand side where you have CIJP, I
yes,
think the operator should be OP, right? Not OK.
Oh yes, yeah.
Okay.
Yes, okay,
Okay,
I'm sorry. That was a dummy index and I might have changed it sometime.
So this was the case about which my question was. Okay, it's fine.
Yes, thank you for bringing that to my notice.
So you say that these normalization conditions give you additional constraints?
So I am not saying, right now I'm not saying that these are additional constraints.
Right, this was my
these
question.
are relations right now, which I don't know the exact structure, so it might be a subset of the conditions that we already have. It's just a different way of approaching, but yeah, I mean, I need to finish this. Like,
right.
There
it might be something that's already in crossing. It's not that you expect
that
there are additional
It's just that we
constraints
are
to the CFT
completely
needs.
using a different approach to like get some relations. Yeah.
Okay, thank you.
I mean, we're now in a normal conformal theory. Sometimes you have an action, like you can have your cover coupling, and then normalization tells you that you need to have a 5 to the 4 as well. So normalization forces you to complete the theory in a specific way. Now here the question would be, if you have a CFT in 4 dimensions that has a dimension 2 operator, could that be a CFT on its own, or the spectrum necessarily has other operators? And then you can keep adding, like, it is possible that to renormalize the theory, you need to add additional operators. And once you add them, then you start bootstrapping the spectrum. What are the, does renormalization bootstrap the spectrum of a CFT, or do you need, because that would be in a sense a more straightforward approach than the this bootstrap equation, which is quadratic, and okay, we now know how to solve it partially numerically. When the other one, in a sense, you start renormalizing, you put still an assumption about the low-lying operators, and then you ask, does the normalization say something about the spectrum, or can I always normalize?
Okay, more questions? If not, let's thank the speaker again.